Guys, yeah, so I'm Hensley Mariathas, so working as a research associate. I don't need to introduce myself. Already Chelsea introduced about myself. So I will go into the session right away now. So introductory SPSS workshop. So before start the SPSS, SPSS is a statistical package for social sciences. So this package will help you to analyze any type of data. So before start the SPSS, I thought it would be nice to start with the data and type of data and the application of statistics. What are the statistical applications could be applied into the data, stuff like that. So we'll get some idea about the data and the application of statistics, and then we move on to the SPSS software to analyze the data set. So, okay, a second. So, here you are. Okay, learning objective of this workshop. At the end of the presentation, participants should understand to recognize different type of variables, method for describing sets of data, and how to display those data using a graphical method, as well as display with the numbers or tables. Numbers in the sense describe as a summary of the data, and if you could able to draw some tables of the data and differentiate between descriptive and the inferential statistics, and how to perform statistical analysis using statistical software called Statistical Package for social science. So in that case, you will have some idea how to start with the SPSS and working with the data, exploring data, analyzing data. The application of statistics, it can be divided into two wide area. One is called descriptive statistics. The one is inferential statistics. These are the two major components in the application of statistics. And applications nowadays arises in many fields such as industry, health, education, right? Uh, and descriptive in the sense you have to summarize your data which was collected for your research purpose, organizing those data in a table form. And inferential statistics in the sense that you need to make a conclusion about the population of interest, right, using a sample gathered from a target population. So these are the main component of the statistical analysis. So we will do this kind of a descriptive analysis as well as kind of an inferential analysis using a statistical software in SPSS for certain type of data. And better to have some idea about the type of data as well. And once you identify before analyze the data, the type of data, then analysis would be more easy, right? So data and variable. So data is a set of information or observations about a group of individual or subjects. This information is organized in the form of variable. So variable is any characteristics of a person or a subject that can be measured or categorized. Its value varies from individual to individual. For example, a patient visit to the emergency department. So in the triage panel, someone will take information from the patient as a registration process. In that registration process, the person involved in that triage panel might get lots of information from the patient, right? That means the patient name, first name, last name, age, and if there are any identification numbers such as MCP card or any other numbers. So they will go with each and every patient will go with the individual ID and sex and the patient body condition, stuff like that, right? So these are kind of first name is one of the variable, last name is another variable, and the age at the time of the ED visit is one variable, and sex is going to be another variable, and the body condition or health condition, right? So for what reason the patient came to the emergency department, stuff like that. So these values should vary from patient to patient at the ED site, right? For example, a simple example is height in centimeters, which varies from patient to person, and sex also might be male or female, those kind of a variable, right? So types of data, once you gather information, you need to know what type of data is this, right? So there are two basic types of variables. One is quantitative, is or sometimes it's called numerical, and qualitative, sometimes it's called categorical variable. So where the variable to which the number is assigned as a quantitative value is called numerical variable or quantitative variable. A variable defined by the class or categories into which an individual member falls is an example for a qualitative variable. For example, height of a person is an example for numerical variable, right? So another variable called sex, right? Male or female, this is an example for a categorical variable. The numerical variable can also be described in a two different way. So number of visits to the emergency department, right? So made by a single patient, right? So zero numbers, 1, 2, 3 kind of stuff. So these are called discrete numbers, right? It reflects a number obtained by containing no decimal, right? Number of injuries, number of positive notes, number of visits to the emergency department. Those are examples for discrete random variable. Discrete variable. And continuous variable reflects a measurement. The number of decimal places depends on the precision of the measuring device. Height, weight, blood pressure, those are example for continuous variable. Okay. And categorical variable defined by the classes or categories into which an individual member falls. So these categorical variables can be classified as a nominal scale or ordinal scales, where the categories don't have any order. For example, say gender or sex, male or female, you can assign number 1 or 2 or 0 or 1 without any ordering, right? So wherever you have a cancer stage, right? Cancer stage, first stage, second stage, third stage, stuff like that. These now numbers give some ordering, right? First stage, second stage, third stage, right? So if they are ordering involved in the category, those are examples for ordinal scale data. And order is not important. An example for a nominal scale, for example, gender, hair color, type of injury, right? And nominal category with an implied order, trauma stage, right? Cancer stage, right? Those are kind of an ordinal scale data type. Okay. So now you have some idea about the qualitative data or numerical data, discrete or continuous, categorical data, nominal or ordinal scale data. So if you know the type of data, then you might have some idea which type of analysis or which kind of a representation of the data as a graphical or whatever could be ideal for display, right? As a summary. So types of variable, also dependent variable, independent variable, say the outcome variable of interest, which changes in response to some intervention or exposure. So mortality, survival, post-op pain, quality of life, these are an example for a dependent variable, right? An independent variable is the explanatory variable that explains the changes in the dependent variable. So that kind of the information, for example, demographics, age, gender, height, risk factors, and drug surgery, radiation, smoking habits are example for independent variable. So this kind of information would be ideal to know where you go for a regression model fitting or multivariate regression model fitting, where you need to identify which variable going to be independent variable and which variable going to be a response variable as a dependent, right? So independent variable mostly called sometimes is a predictor variable, and dependent variable is your outcome variable. Data set and data table. Data set is data for a group of variables for a collection of persons. Data set organized into a table with one column for each variable and one row for each person, right? So as I look at the typical data table here, right? So there are 20 observations in this data set. Altogether, 1, 2, 3, 4, 5, 6, 7 variables involved in this data set. Age, BMI is a body mass index, FF number, fast food, number of fast food taken, temperature, a gender of an individual, exercise level, and questions, right? So each patient went through a questionnaire and their answers, right? So given as a Likert scale data. And if you consider each variable, right, so age variable is an example for a discrete variable, right? And BMI, body mass index, has a decimal numbers, is an example for a continuous variable, right? So FF number is an example for a discrete type of variable. Temperature is an example for a continuous variable. Gender, especially a nominal scale variable as a category. Exercise level is 1, 2, 3, right? The low, medium, or high stuff, ordinal variable, and questions as a Likert scale data or variable, right? So these are the variables involved in the previous slide: age, BMI, and the weight, body mass index, right? That is measured in the kilogram per meter square, because weight over height squared, right? So it says FF number, the average number of times eating fast food in a week, right? And temperature is an example for continuous. Gender numbers for 0 for male and 1 for female, right? You can keep it as a male female as well, or you can number 0 1 as a nominal scale, right? Exercise level, 1 for low, 2 for medium, and 3 for high. So 1, 2, 3 is in an ordered format. So exercise level is an example for ordinal scale data, and the question is an example for a Likert scale data. Okay. If you have any questions, just type it into the chat box, then I will go through the questions as well, right? Okay. So now we'll move on to the SPSS environment, right? So we discussed some kind of a data type and the types of statistical application. And the SPSS utilizes multiple types of windows or screens in its basic operations. Each window is associated with specific tasks and types of SPSS files, right? So data file SAV, output file SPO, and syntax file SPS file, right? So these are the main 3 files associated with SPSS. One for data file, one for output file, and the syntax file. Syntax file in the sense that where that means the SPSS has a syntax editor to write some commands, right? So it's kind of a programming window, right? You can write multiple commands to execute the file, right? The windows include the data editor, output viewer, syntax editor. So what is data editor? When you go into the data editor in the SPSS, I will go through the SPSS in the next slide. So the data editor window is the default window and opens when SPSS starts, right? So you can go start button and click IBM SPSS, then you will get the SPSS window editor window. This window displays the content of any open data files and provides drop-down menus that allow you to modify and analyze data. The data are displayed in a spreadsheet format where columns represent variables and row represents cases, right? Look at the data editor window. The spreadsheet format includes two tabs at the bottom labeled data view. Here one is data view and the variable view. The data view tab displays the open data set. Variable appears in columns and cases appear in rows. The variable view tab displays information about variables in the open data, but not the data themselves, such as variable names, types, and labels, etc. Okay. And the output editor, output viewer. So let's open a. Give me a second. Let's open a SPSS file first. How many of you are having SPSS in your computer? Any one of you are having SPSS in your own computer? Yeah. So if you have a computer, if you have SPSS, just follow with me, right? Can you able to see my SPSS data view shared in the shared window? Okay. So look at this one, data view and the variable view. So in the variable view, you can name the variable view, right? And the type of variables and with the decimals, labels if necessary. Fill up this stuff and go to the data view and enter the data from row by row, right? Okay. Okay. And I will come to the output window later, right? And this is the syntax editor. Syntax editor is a programming language unique to SPSS that can be used as an alternative to the drop-down menus for data manipulation and statistical analysis. So this editor will help you to write down the commands, right? So mean of the variable, and if you want to do some calculations, arithmetic calculations, and create the new variable, and that all the syntax editor also help you to read or input the data into the SPSS as well. You can create the variable 1, variable 2, variable 3, and let the syntax editor to type the data in a row by row, and the end of the data entry, type the execute command and select all and run the command. You will get the appropriate data in your data editor, right? The syntax editor window is where users can write, debug, and execute SPSS syntax. To open a new syntax editor window, click File, New, and Syntax that, and choose the file where it's located. Okay. And here, look at that, some kind of an programming language written in the syntax editor window, right? So this once you select all the commands and run it, then you will get the output corresponding to these commands, right? Okay, as I said in the data editor window, how we'll see how to create the data, right? So I already gave some some data for you guys, right? Okay, okay. For example, yeah, if you don't mind, can you open the data file, file name as cholesterol text file, right? Do you have that file with you? So go to the file and open. In the open, so look at the sorry. So go to the import data, right? So I'm trying to import data because open in the sense if you press reset data, then you have to have a SAV file. I am trying to import data because look at the import data. That will help you to import any Excel file, CSV data, text data, SAS data, Stata data, DBase, Lotus, stuff like that. Okay. So in this case, I am trying to import the text data, and the text data is available in, where is my location? I need to pick my location. Okay, look at this cholesterol and open it. And when you click open, then you will have a bunch of information, right? So we have to put and press next, 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 press finished. So the whatever the command you executed will appear in your output window. This is your output window, okay? And I do have one output window as well as the data editor window. This is our data editor window, okay? Have you got the data in your screen? Anyone having any issues, let me know. Okay. It's still opening. I don't know why it's take that long. Okay. Okay, while doing that, the data creation in SPSS. So once you gathered information, right? Now you have information in your hand, need to be entered in somewhere in statistical software in order to get the data analyzed, right? So in that case, you need to know how to enter data into the SPSS, how many variables involved in the data that was collected, and how many number of information that you have, stuff like that. Look at this example. The data in here, the table below is the data of clinical outcome measurements for percentage of mannitol gut permeability in patients with AIDS, AIDS-related complex ARC, asymptotic HIV positive or HIV negative. And the status of HIV diagnosis are these four, right? So in this data set, in order to perform an analysis on this data set, before doing the analysis, first you have to transform this data into the SPSS. So in the SPSS, how many columns that you are thinking to allocate to enter this data? Do you need 4 columns or 5 columns, or you need only 1 columns? How many columns that you prefer to enter this data into the SPSS in the data editor?
4.
4? So
Yeah,
why
4
4?
variables, 4
Sorry?
4 variables.
You have 4 variables? Any other numbers?
I mean, observations are more, but the variables are 4.
Okay. So what is these four variables? There is a status of HIV diagnosis, right? The status of HIV diagnosis has 4 levels, right?
Oh, right.
So AIDS, HIV negative, HIV positive, and ARC, right?
So that's
So
ordinary.
in this
One.
case, you need only 2 columns, right? So one for the measurements and one for the status of HIV diagnosis. Am I right? Okay. So create 2 columns, one with the measurements, so percentage of mannitol gut permeability in patients, and the second column need to be status of HIV diagnosis, right? So enter these measurements, all these numbers in one column, and the second column you have to have 1, 2, 3, 4, or you can label those numbers later: 1 for AIDS, 2 for HIV negative, 3 for ARC, 4 for asymptotic HIV positive. Okay, does that make sense?
Yes.
Yeah.
Sorry, I got confused. Yeah, okay.
It's okay, no problem. Yeah. So then import data files. So otherwise, if you saved in somewhere as a SAV file or a text file or Excel file, right? Or CSV file, any type of data, you can import it to the SPSS by identifying the sheet, right? So in which sheet your data entered, right? So now select the sheet exactly, sheet 1 or 2 or 3, and then we import the data into the SPSS and do the rest, right? So working with data and working with management. So exploring data, before go to the descriptive statistics, and I would like to go to this. Let me, okay, we'll come to that. So I gave some informations here how to working with the data, right? So working with the data in the sense you can create new variable, right? You can add any new variable into the data sets, and you can create the new variable using any two existing variable in your data sets, right? Using a mathematical transformation or whatever, right? For example, a date of birth and date of visits or something, sorry, date of admit to the hospital, then you need to calculate your age, then subtracting those 2 dates, you can get the age at the time of the admission, right? Stuff like that. And managing data. So managing data, you can have a look of the data, and wherever missing information is involved, check with the data, and if you could find the missing value and replace the missing value, otherwise ignore the whole row and do the analysis with the rest of the data, right? So once you enter the data, then descriptive statistics for continuous variable as well as descriptive statistics for categorical variable should be done using any kind of a method available in the software, right? So we will discuss that one using a data set. And descriptive statistics for one numerical variable is a step-by-step process is given. Just go over it and you will understand more and more how to handle those kind of a situation, right? So before the analysis and stuff, so this is an example. What are the inferential statistics for association? What kind of inferential statistics for comparing mean? Depends on the sample, 1 sample, 2 sample, or paired sample, or one-way ANOVA. You have to think about what need to be carried out, right? So it depends on your data in your hand. Okay, look at the practical problem. Yes, the practical problem. Hi, here you are. Okay, so the practical problem, we are trying to manage the data. Okay, then so here the cholesterol text file contains randomly collected information from 200 patients, right? And we import that data. The first using a create a new variable sex. Actually, you don't need to, in this case, it's one of the demographic information of the patients, right? So information of the patient, this is the data set, right? We do have 200 information, right? So now the first thing is you have been asked to create a sex variable. So normally when you collect the information, you have to get this sex data, but the purpose of introducing generating a sex numbers for sex, or either 0 or 1, give some idea how to generate some numbers, right? So binary numbers that might help you to allocate some patients into control group as well as treatment groups. How to randomize these patients, right? So into the control group and the treatment group. So in this case, what I am going to do, I am going to place some numbers for a sex variable, right, into this data set. In order to place some numbers in the sex, in the sense, take 0 as female, or 1 for 0 for female, 1 for male. So 0, 1, 2 numbers, you can generate these numbers by using some random generation. And these two numbers are especially used as a dichotomous variable or binary variable. In order to generate these numbers, create a new variable sex and generate random numbers as 0 for female and 1 for male. To do this, click transform, right? Okay, are you following? Click transform and compute variable, right? Compute variable. And under the compute variable, on the left hand, type a name for the target variable. What is the target variable in here is sex, right? Which is the new variable that contains the random numbers, either 0 or 1, right? So usually when the data collection, you will have a sex variable, but this is an idea to generate some variable with binary numbers 0 and 1, right? Okay, give you an idea how to do the generation of numbers. It doesn't mean only 2 numbers, you can generate any other numbers as well, between 0 and 9 or any other random generation tools, right? So which is the new variable that contains the random numbers, either 0, 1 to be generated. In this example, we call that variable as sex, all right? So what is the numeric expression, right? In the numeric expression, you have to get the random number from function group, right? Random numbers. What could be the ideal distribution to generate the binary numbers, either 0 or 1? Any guess? So what about there are some random variables are here, right? Bernoulli, beta, binomial, Cauchy, chi-squared, exponential, f, gamma. What about the Bernoulli random variable? Have anyone heard about Bernoulli random variable? Bernoulli random variable, in the sense, is kind of a random variable with 2 outcomes. That means when you toss a coin, you will have a head or tail, or success, failure, something like that. So once you click this, it will give a syntax for that, right? So random variable. So double click it, it will pop up into the numerical expression. I'm going to use the success probability as 0.5, right? And press OK. Then you will get some information in the output window. Minimize this. Now look at this sex variable as 1 or 0. It has only either 1 or 0. What I am going to do is I am going to eliminate the decimal numbers, go to the variable view window and go to the selection and look at the decimal, change into 0 and press, then go to the data view. You will have a sex variable with 1 or 0. Okay. Now
So
what
when
I'm going to do is I'm going to change this 1 for male and 0 for female. How do we do that?
going
So
to
in order
variable
to
window,
do, sorry,
going to variable window.
you need, oh, you want to see the variable window?
No, I mean if you are going to nominate one for a female
Yeah,
or
yeah, go to the variable view and simply you can values that using the under the values, go here and put the values for 0 and label it as what? Female, right? Okay, female. And add that one into the box, and then what else? 1, and go to the label this one as male, right? I'm not sure how many of you are following with SPSS. Press OK, go to the data view, and you can check this one by pressing this icon, values labels, 1 0 variable. Okay. And also I would like to, what about the smoking status? Right, smoking, cigar, non-smokers. I want to keep this one as smoking.
I have a question.
Yeah, sure.
So when you created this this variable sex, so you use the function transform, right?
Yeah.
You could have directly gone to the variable view and then created the variable. Would that be okay?
Where to the to mean generation?
How did you? I mean, why did you go to transform function to create? That's how you create a new variable.
Yeah, because because you can create variable here. Otherwise, you have to enter manually, right?
Okay. Okay. Right.
You know what I mean? I didn't enter any 1 0 manually. I generate some random
Right.
numbers, either
Okay.
0 and 1, right?
Okay. Right. Right.
Because it doesn't mean these numbers you will get the same sex in your data set as well if you do the same thing, right?
Mm-hmm.
Because it's random generation, right?
Right. 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 Right.
For
Okay.
example, in my case, the first individual with the male, sex with male, right? So for example, for your case, it might be female, right? It's a random generation, right?
Yes.
So that's what I said. To be honest, this is one of the demographic information from the patient prospects, right? So you have to have this information when you collect all other informations, age, height, and weight, right? But
Right.
I gave this idea to understand how we can generate some other numbers to handle the randomization if you are really wanted to do some clinical trials where patients need to be allocated into control group as well as the treatment group, right? So this
Right.
kind of a generation will help you to do that. So, okay.
Okay. Sure. Sure. Yeah.
So if you do have a sex in a separate sheet with you, then you have to enter that one manually using the variable view, create the sex and go to the data editor and enter the information in here manually, right? So I just did a simple command using a transform, right? And using the random variable Bernoulli trial with the success probability 0.5, that's P. So using the sex, if you are interested to get a frequency table, right? Yeah, go to the analyze and descriptive statistics frequency table. For which variable you are interested to get the frequency table, select the variable and press OK. Then you will have information here, right? So 98 individuals with the female people and 102 people from the male group, right? And the percentage, valid percentage, and the cumulative percentage also, right? This is the one way of representing a table for sex variable. Okay.
Yep.
So It's close to, because equal numbers, right? 98 and 102 is almost close numbers, right? 50-50 chances, right? So why it should be? Because I chose the Bernoulli success probability as half, right? So in your group, when you have when you select the p-value in a different value, for example, so 0.75, then you will get the different numbers, right? All depends on the probability p. Okay. So this is one way of representing a sex variable. Sex variable is a categorical variable. Also, you can do some graphs as well, graphs, right? Legacy plot, legacy diagonal. You can do some pie graph or bar graph. For example, pie graph, right? Define and define the slice. Select the variable, not this one. Cancel. Go to the summarize for group of summarize for separate variable values of individual cases. So define the sex variable. Press OK. There's the file graph. It's processing. Please take that longer. Oh no, it's I took the wrong one. Graphs. Slice represent. Cancel. Analyzing graphs. Group of cases. Define slice by X and here you go. Okay. This is not the appropriate one. Okay. Okay. So one for blue color for female and red color for male, right? So I do have only two levels of sex, right? It's male and female. That's why I am getting. So you can have a bar graph, any other graphs, right, as well. Okay, now go to the, what is the next question here? And using SPSS, create a new variable, define values for label, compute a new variable BMI, body mass index. Okay. So how to create the body mass index? So what is body mass index? To do this, click transform, compute variable, right? Transform, compute variable. And the variable name, I would say body mass index. Okay. What's the expression for the body mass index? Anybody? So I assume the weight is there, right? I already expressed the body mass index calculations. The weight over height square, right? So weight over height square. Assume the weight, weight is weight over height square. Height is in, say, for example, weight is in kilogram and height is in centimeters, right? Assume that is measured in centimeters. Then what would be the expression, numerical expression for the body mass index? Any idea? So weight, what is that? Weight and weight over height squared, right? So weight over height squared, height was measured in centimeters, then you have to divide by 100. So 100 into 100 divided by the weight, the height. Square, right? Squared is given by this form. Okay. because denominator is height over 100 squared. So that's why the 100 into 100 comes into the numerator. The press OK, then you will get the body. Sorry, what is the sequence of operation from this?
I have a question.
Yep.
Can't we convert the height here directly into meters before writing this expression? Like as a novice who might not be able to create this numeric expression, isn't there any way
yeah,
to
you
convert
can do that as well. Yeah. You can
Okay.
convert this height, whatever that means. For example, you can transform the data, compute variable, right? Say same expression, select the variable itself, right? And height, and save the new variable in this with the same variable name, right? Okay.
I get you. Thanks.
Is that the one you want to do?
Yeah, that was what I was asking.
Yeah, you can do that. Yeah. Okay.
Sure. Thanks.
But I didn't do any changes in my original data set. I keep that one as it is. I want to create the BMI in a different manner, right? Okay. So weight into 100. Oh, sorry, this star here, right? Okay, that's what. Press OK. Now look at this. Okay. Now you have a body mass index. You can change the decimal numbers if you want. You can increase the decimal numbers into 2 or whatever, right? Now we create 2 new variables X by using the generation technique and BMI using the formula. Okay. We ended up with the body mass index. Even though sometime in the statistical analysis, numerical variable could be classified into some categorical variable, right? As once you know the boundaries, you can categorize into 3 different groups. That's what I'm going to do in the next expression, right? So defining the computer new variable BMI body mass index, break down the continuous variable BMI as categories: underweight, normal weight, overweight, right? So there are, and obesities as well, right? So that means the body mass index going to break down into 4 different categories. It's an example for a categorical variable. How do we do that? Okay. So so now we computed body mass index, right? Do you have any questions?
Is it easy to use continuous data or nominal data?
For the categorization?
I mean, computing anything, or obviously, I think for inferential, you will have to keep it as it is, right?
Yeah, for this case, BMI, it depends on your research interest, right? So if you plan to keep this one as it is, you can do any continuous analysis on that. Or otherwise, if you want to break down this data to see how many percentage of the people are obese people and how many percentage of the people are underweight people, stuff like that, okay?
Right.
For that, you can break down this data into a different category as a nominal or ordinal, right? So in this case, if you break down into the categorical variable, that is going to be ordinal, right? Because it's order involved in this data, okay?
Right, yeah.
Make sense?
Yes, please.
Okay, so break down the continuous variable BMI as a category underweight. To do this, you go to the transform and compute a record or record into different variable, right? Select this and you will end up with the record into different variable, right? And for which variable that you are going to record a different variable is a body mass index. Go to the old and new values, right? select the variable body mass into numerical variable and to output variable. In the output variable box, you will see, click the box named here, right? So what I'm going to do is type in BMI category, right? This category, and label it as body mass index in category. Okay, change it. Then click old and new values. All right. Based on the cutoff values on the old value box, create a new value and add into old new boxes. From here, ranges from lowest. What is the, check this one. What is the first value? It's 18.5, right? The lowest value 18.5, and value I am going to put that one as 1 at that value. Second one is 18.52 through 24.9, and the value going to be 2 at that one. Third one, 25 to 29.9. And this is going to be the third group, and the fourth group going to be ranges value through highest value is 30, right? It's going to be 4. Now press continue and then press OK. Oh, what's that? Something was missing, I guess. Let's recording to new variable. What is that? Let me check. Oh, sorry. Transform recording to different variables. Old and new. Cancel it. Reset. Body mass index. This is there. All right, give me a second. I will erase this one. Transform record into different variables, body mass index, BMI. BMI category. Change that one, old and new. The lowest from 18.5, right? Sorry, 18.5 is going to be the first class. Add, and the second one ranges from 18.52 through 24.9. The value is going to be 2. Third one going to be 25 to 29.9, and which is going to be the third category at that one. Fourth one is about 30. Press OK. Oh, why is that? 25 is not coming here. This should be 25.9, should be normal weight. Is that right? Why is not? Let me redo this one. Clear. Transform compute variable. Body mass index. Press OK. Okay. Them into different variable. Category. Body mass index. Category. Change. All the new through range 18.5. Oh no. Oh, sorry. 18.5. This one. And this one going to be, the second one going to be 18.5 to 24.9. 24.9. It's going to be.
Shouldn't it be 18.6 to 24.9?
No, 18.5 because the lower value won't be there, right? So it's in this case it starts automatically. It starts from 18.6 to 24.9, right?
Okay. Okay.
So left one is open, okay, and third one is 25. Oh, so maybe let's check with that 18.5. So 25 to, okay, 24.9, 25 to, oh, it is 20, maybe this is, you are right, yeah, it's 6. Change into, remove into 18.6 to 24.9, going to be 2. This is 25 to 29.9 into third row, and this one going to be the 30. It's going to be fourth. Oh, still having a problem, right? Why is that? 24.9. Yeah, it should be there.
Why is it showing decimals when it's a categorical variable?
Oh, you can change that one. It's okay.
Okay, okay,
This
right.
is the decimal, right? Here you can change it.
Okay, right.
Okay. Yeah. So why is not working here? It should be 3, right? There should be 3.
Do you need to mention decimals when you're creating, transforming?
For which BMI?
Yeah, for BMI categories, the new ones. Do you need to?
You can change it later, but automatically by default it takes 1 decimal places,
Mm-hmm.
right?
No, I mean to say when you're actually writing the code, do you need to
Okay.
specify 18, like you said, 18.6, and then for 30 it's only 30. Do you need to mention 30.0?
30. No, you don't need to. Yeah,
Okay.
that's okay because you are dealing with the BMI variable, right?
Mm-hmm.
The BMI variables are numeric, right?
Mm-hmm. Yeah.
You know, so automatically SPSS knows what was that. Okay.
Okay. Yes.
So let me check why it's not working over there. Okay. Give me a second. I'll open. Oh no, cancel it. File, open, import data. Our data is in a text file format. Tester. Open. Next. Bear with me, I will be back soon. Right. Okay. Transform. The random numbers Rn. Complete variable. Okay. Where's the compute variable? That was
Excuse me, I just recognized something. I just changed the end of the BMI values. I set it up for two decimal numbers, and it works.
into how many decimal numbers? 2 or 3?
2. Just I didn't set up here anything. I went back to the BMI CAD categories, and I set it up the scales. I'm not sure that I use this for 2 decimal numbers, like from 18.51 till 24.99, and the next one is from 25 to 29.99 or so, and it works. That's
Give me a second. Yeah,
that way.
It should work, I guess. Let me.
I just tried.
Let me redo again. Yeah. Alternate variable.
It works
Give me a second. Yeah. It's old and new. Okay, what's that? This is a range 18.9, right? First one.
Yeah, it's
18.5, right?
I set up the lowest one, 18.50. That is the one.
Oh yeah, give me a second. Yeah, 18. And then the second one going to be from range to
18.51.
no 20. Oh yeah, 18.5. 0 to 24.9 is
Yeah,
going
but 18.51 to
yeah, and then
24.99.
24.9, 25 to, right? 25.
And the third one is 25 to 29.99.
99.
Because so I just recognize that probably because of the decimal, as someone
maybe.
mentioned earlier.
And the last one going to be 30, right?
Yeah, but
only few will causing a problem, I guess. Yeah. Okay. Let me see what's going on.
I mean, now I didn't have any missing values if I use this one.
Yeah. So yeah, I don't know why it's causing a problem. It should work, I guess. Anyway, what I'm going to do is remove this one. Okay, this is from 18.9, 18.5, right? Let me see. What's 18.5?
I set it up all of them nearly just
no, 18.5, right?
18.5, yes.
One and add this is one going to be 18.56 to 24.9.
18.51 till 51.
Oh, sorry.
Yeah, till I set up 24.99.
At 24.99 to 20. Sorry, 20.
I set up the second one as till 24.99, and I started the third from 25th 00.
Oh, maybe. Oh, sorry, this one, right?
Yeah, that should be 24.99, the second one, in 18.51 till 24.99. That should be the second one.
And this one 30.25.
It should be 25.00 and till 29.99. Yeah, and the last one should be
30.
from 30. And I think this worked.
But the earlier one also should work anyway. As far as this works, it's fine. Okay.
I don't really understand why it didn't.
It should work, I
it.
guess. Anyway, yeah. As far as you categorize this, that would be good enough, right? Okay. Okay, is that clear? So now what I'm going to do is I want to replace this one with the exact names for that, right? Go to this. What is the value? 1 is going to be overweight, sorry, underweight, right? And the second one going to be normal weight. Third one going to be the overweight. Sorry, and the last one, fourth, going to be obese. Okay, obesity. Oh, look at this. So rather than keep 1, 2, 3, 4, better to label them now those numbers. Then when you go to the analyze descriptive frequency table for the categorical data, sorry, take this one off. So you will get the nice table for that, right? So only 5%, not 5%, 0.5% are underweight patients. So 18%, 9% of the patients are overweight patients, right? So only 47% of the patients involved in the data sets are normal weight people, right? So this table, look at the BMI category table, provide the brief information about your data set, right? And also you can have a bar graph as well to compare the weight category between the BMI category between the categories list, the bar graph, Where's the bar plot? Here you go. The simple bar graph. For a category axis, body mass index, press OK. Say, so this is always nothing, there is no, right? So only the normal weight people are with the high rate in your data set, right? Okay, this is a kind of a describe your data set in a graphical manner as well as the table format. So you have, if you take the descriptive statistics for the BMI, the raw data with the continuous scale, go to the option, you can find some kind of a mean, standard deviation, variance, maximum, minimum, maximum, right? And continue, press continues. You will get the descriptive summary of the body mass index itself. It's a continuous variable, right? So mean body mass index among 200 patients would be 25.53. On average, 25.53. It's an overweight patients, right? Right. So on average, the data set on has overweight patients, right?
So do you mean 25.3 is the actual number, the actual weight of some people, right?
No, on average, right?
Yeah, on average, that is the weight, right? It is not the percentage.
Yeah. So if you want to make some population estimates based on this data, right? So average population of BMI population, average patients with the BMI going to be 25.5, right?
So we are not saying that it's 25% of the population. It's the actual weight.
No. It's actual, not percentage, right? It's exact BMI value, right?
Okay, right.
Average value, right?
Okay.
So look at this descriptive statistics. It's totally summary of your data, right? There is no percentage in here, right?
Yes.
Okay. Any questions? Okay. So that's a way you can break down if the continuous data necessary to categorize. Otherwise, you can do analysis using the raw data as it is continuous with the continuous value. Okay. Now we'll see how to do inferential statistics, a kind of a one sample t-test or two sample t-test, paired sample t-test, stuff like that. So one sample t-test. What was that? You are doing some hypothesis testing or confidence interval or whatever the inferential statistics point estimating the population parameter or hypothesis testing of the population parameter, right? So in that case, we would like to pull the data of MRI records, right? So research team studies subject with medical collateral ligament MCL and anterior cruciate ligament ACL TS between February 1995 and December 1997. 17 consecutive patients with combined actual ACL and grade 3 MCL injuries were treated by the same physician at the research center. One of the variables of interest was the length of time in days between the occurrence of the injury and the first magnetic resonance imaging MRI. So these informations are given in number of days. The research team wished to know if they can conclude that the mean number of days between injury and initial MRI is not 15 days in a population presumed to be represented by this sample data. So in this case, the research team would like to test a hypothesis is on a number of days, on average number of days, mu is equal to 15, versus the research hypothesis going to be mu not equal to 15. All right. So in order to conduct this hypothesis testing, do you have any questions on this data set? If you don't have any data question, then I can pull the new data set, open the data. So this is a data diagnosed to MRIs SAV file. Just open the file, then you will get the 17 information here. All right. Once you pull the data into the SPSS to carry out one sample t-test, go to the analyze. So compare means, right? It's an inference. So compare means, select the one sample t-test, and for which variable that you are interested to carry out the test, pull the data variable into the test variable, and the test value. What is the test value here?
15.
It's going to be 15, right? So mu is equal to 15 versus mu not equal to 15, right? And the option, go to the option. So confidence interval percentage, by default, SPSS takes as a 95% of the confidence interval. That means you are trying to test this hypothesis at a significant level. Alpha is equal to 0.05. Is that okay?
Yeah, but so why are we doing t-test?
That's a good idea. How many samples are here?
17.
17, right? So 17 samples are here. Is it sufficiently large enough to do the z-test?
No, it has to be, I think, more than 30 participants, right?
Yeah, and also in order to, in the case of doing a t-test, you have to assume this data came from a normal distributed population, right?
Right.
So there are certain assumptions, right? So the t-test, by default in SPSS, every test is conducted using a t-test. Doesn't matter if it is a z-test or t-test. Z-test is meant for large sample case, right? So most of the situation, the population parameters are unknown, right? Even though mean or variance, those are unknown. Even though sample size is small, variance is known, then you could able to use z-test if the samples drawn from a population where the population distributed as normal.
So do you have to check for normal distribution first then?
Exactly, yeah. So you can check that one in later. QQ plot or probability plot or histogram will help you to check the normality assumptions, right?
Yes.
Okay, yeah. So here, because in order to conduct the t-test, definitely these samples should come from a normally distributed population. Otherwise, you can't use the t-test, right? Because one of the major assumptions in order to carry out the t-test, right? And the variance is unknown in this situation, right? Assume variance is unknown because of the population. If the variance is known, you can use the z-test, right? Even though sample size is small. Okay. So if you are planning to do this kind of an analysis manually, yeah, check those stuff, right? So with the data coming from a normally distributed population, or what would be the sample size? It's large enough, sufficiently large enough to conduct the z-test or t, right? So why we use z-test is because of the central limit theorem, right? So central limit theorem for a sufficiently large sample size, the sampling distribution of the sample mean is approximately normally distributed, right? Then you can simply use the z-test when the question arises when you have a small data set, okay? So in this case, if you really wanted to do a test for a different confidence interval, you can change that number into 99 or 97 or 90. Keep this as it is, continue, and the press OK. Then you will get the output here, right? look at the one sample statistics. This table give you a descriptive summary of the data, diagnose underscore MRI data with the mean 13.29 standard deviations there. And the second table will give you a output for the hypothesis testing. And the t-value here is a minus 0.791, because the test statistics was used in this case is a t statistics, right? X bar minus mu naught under the null. This t statistics is upon square root of n follows student t distribution with n minus 1 degrees of freedom, right? So we had a 17 observations, so n is equal to 17, n minus 1 is 16 degrees of freedom. Is it a two-tailed test or one-tailed test? Anyone?
One tail, I guess.
One tail? Okay. Because the researcher wanted to know whether mu not equal to 15, right?
Yes.
So not equal to 15 in the sense it leads to in the either side of the sampling distribution, right? It's maybe in the upper tail end, it may be in the lower tail end. So these are the area going to be your rejection regions, right?
Mm-hmm.
So under the null, reject the null going to be the observed significant value. It's maybe either upper tail end or in the lower tail end. Okay. So it's all depends on your alternative hypothesis. If it is if it is in not equal or less than or greater than, right? Any one of three format, right? So not equal, less than, greater than. But null is going to be equal, less than or equal, greater than or equal, right? These are the symbols could be assigned to the null hypothesis, and the alternative hypothesis could be not equal, less than, or greater than. If it is mu less than some value, going to be the left tail end, mu greater than some value going to be in your right tail end, and mu not equal to some value going to be either side of the tails. Okay.
So a one-way t-test, single t-test is performed in which case? Like, can you give an example?
Yeah, it's all depends on the significant value. What is the significant value here? Two-tailed significant value is the p-value, right? The observed p-value is a probability of a test statistics. Any value, extreme value bigger than the test statistics value, right? Okay, so that is the p-value. In this case, your p-value is a two-tailed test, so that is the p-value. You can compare that p-value with the level of significant alpha, which is in our case 0.05. If any small p-value leads you to reject the null hypothesis. Okay. In this case, the p-value, two-tailed p-value 0.440. That's almost bigger than 0.05, right?
Right.
The bigger than 0.05 means your calculated value somewhere falls in the non-rejection region, right?
Okay.
The non-rejection region means you don't have enough evidence to reject the null hypothesis. Am I right?
Yes.
Yeah, therefore in here, we don't have enough evidence to conclude mu not equal to 15, right?
Yes.
So that indicates we don't have we fails to reject the null hypothesis, right? So that is the interpretation of this table, okay? So if it is a one-tailed test, then you have to have a p-value half of the significant value, right?
Okay, 0.025.
Sorry?
0.025.
0.220, I guess, right? Half of the value, what's that? P-value, 0.220, right? Even though that is smaller than 0, bigger than 0.05, right? Okay.
Yeah, okay.
So that's a way, because the t-test output, any output given by SPSS is for two-tailed test. You have to make sure whether your researcher's hypothesis is one-tailed test or two-tailed test. Then the p-value, based on the p-value, you can find the one-tailed test p-value, right? Half of the significant value going to be the one-tailed test p-value, and compare that value with the level of significance and make a conclusion, make a decision and write the conclusion. Okay.
Okay.
And the confidence interval, there are three ways, because I didn't do any manual calculations here. Manually, if you want to do this exercise as a manually, first you have to calculate the test statistics value and compare that test statistics value with the critical value. The critical value here is T alpha by 2, because alpha is 0.05 and alpha by 2 is equal to 0.025 with n-1 degrees of freedom. And this critical value can be obtained from a student T distribution table, right? And find that T distribution T value, that is going to be plus going to be the right tail end critical value, minus going to be in your left tail end critical value, because it's a two-tail test, right? So any value, test statistics value beyond these numbers indicates to reject the null. Otherwise, you don't have enough evidence to reject the null, right? So that is one way. Second way, you can conclude based on the p-value, right? Observed significant value probability, right? This p-value is smaller than 0.05 level of significance leads you to reject the null hypothesis. Otherwise, you don't have enough evidence to reject the null hypothesis, okay? And look at the confidence interval. Here, the confidence interval is given for a difference, right? What do you mean difference is mu minus 15, right? So mean minus 15 always lies between two numbers, minus 6.25 and 2.86. So in order to conduct the confidence interval for the population parameter mean mu, you what's that? Analyze, sorry. Compare mean, one sample t-test. In this case, your target value is going to be 0, and then get the, so this is the confidence interval, right? 95% confidence. Look at the last two columns, right? 95% confidence interval for population mean mu, because test value is 0. So mu always lies between 8.73 and 17.86. So this is the confidence interval, right? So does this confidence intervals contain 0?
No.
No. So in this case, mu is equal to 0 versus mu not equal to 0 will be rejected, right?
Yes.
Okay. And mu is equal to 0 versus mu not equal to 0 will be rejected. And at the same time, look at the p-value is very small, right? It's small in the sense this p-value is less than or equal less than 0.05, right? Indicates the calculated value falls in somewhere in your rejection region. As a result, reject the null hypothesis in favor of alternative hypothesis, mu not equal to mu naught. Okay. So this way, you could easily conduct the one sample t-test. And similarly, we can do the two sample t. Any questions? So doing analysis is not an important, right? Somehow you could able to get the output, but the thing is you have to interpret the output table, right? And make a conclusion based on the analysis. Okay. Now go to the next data. What is that? Two sample test. Open the data. Does anyone have any questions? Yeah, because the earlier case, the test value was the hypothesis mu is equal to 15 versus mu not equal to 15. That was the researcher's hypothesis. Dr. Server. Okay.
It was in the question, research question.
Sorry, it was the earlier question. Earlier was the one sample t-test, right?
No, I mean to say number 15 comes from the research question.
Yeah, that was the population value, right?
Yeah. It's on the presentation.
Okay, yeah. Let me see. I can show that. Here you are. This number, right? The team wished to know if they can conclude that the mean number of days between injury and initial MRI is not 15. That was the null hypothesis, sorry, alternative hypothesis, not equal to 15. As a result, these two statements are mutually exclusive statements. Therefore, you need to find out the complement of this, that is going to be mu is equal to 15. As I said, your null hypothesis can take any symbols equal, greater than or equal, less than or equal. And your alternative hypothesis is going to be not equal, less than, or greater than, in order to explain those two statements are mutually exclusive statements. Okay, so one is going to be complement of the other, right? So the number came from this research question, right? So that's why I put mu is equal to target value, mu is equal to 15. Okay. Look at the second case, measurements of gastric secretions of hydrochloric acid in 60 normal subjects and 10 ulcer subjects. Okay, in this case, test at 5% level of significance if the mean secretions is smaller for normal subject compared to ulcer subjects. Mean secretions is smaller for normal subjects compared to ulcer subjects. So if I say mu n for normal group and mu u for ulcer group, what would be your hypothesis, researcher's hypothesis? Mu n must be less than mu u, right? Okay. So mu n less than mu u, that was the alternative hypothesis. Then your null hypothesis is going to be mu n greater or equal to mu u. Okay.
Yeah. Yes.
Is that clear?
Yes.
Okay. Now,
is it possible for you to write this down? I mean, show it in a.
yeah, because I don't have a proper tool to write it down. Very sorry. So I do have one in the presentation, but it doesn't work in this slide. I don't know why.
Okay,
Sorry
that's
about
fine.
that.
Thanks.
Yeah. So mu u is the normal group the mean, and mu u is the ulcer subjects group mean, right? So we are comparing these two means. Then your HA going to be mu and less than mu u. As a result, your null going to be mu n greater or equal to mu u, all right? So we'll see how we can handle this situation in our nitric acid. This one, right? 16 and 10, right? Okay. This labeled as normal and ulcer group and numbered with a 0 and 1, right? So in order to conduct the two sample t-test, go to the analyze, compare means, independent sample t-test. So what is your test variable? It's a quantitative variable, right? Okay. A numerical variable, select that one and go to the group. Which one going to be a group? Look at this symbol, right? This symbol indicates it's a nominal group, right? Look at here in the variable name also you can find that. Selecting here and define the group value. Group 1 is going to be 0 and group 2 going to be 1. Continue. Do you have any idea to change the confidence interval percentage if you are going to do this? Because the problem is you ask to conduct the 5% level of significant, also obtain 95% confidence interval for the difference in the. So keep the confidence interval as 95%. Okay, press continue, press OK. Look at this. Okay, this is kind of a different, interesting. So in the T2 sample t-test, usually when you carry out by hand, you have to assume the samples came from a population, and the population must be a normally distributed population. Both, right? Both should be normally distributed. And those two groups are independent groups. And the population variance among those two groups assumed to be equal, right? Okay, so look at the group statistics. For normal group, we do have 16 observations, and means given, standard deviation, and the standard error of the mean. And the standard error of the mean is the sampling distribution, the standard deviation of the sampling distribution of a mean, right? That is standard error of mean. That is sigma x bar, right? With sigma x bar in here is sigma over square root of n, right? That is standard error. And also group has, we do have 10 individuals, and mean, standard deviation, and standard errors are given. Look at the independent sample t-test. Before go to the, interpret the results, look at the first two columns, right? The first two columns give an idea about the variance, right? Levens test for equality of variance. This gives you an idea whether the variance are equal or not. So in that case, variance can be tested using F distribution, right? F distribution is widely used as test statistics to make a conclusion among the variabilities, right, between two groups or more than two groups. In the ANOVA also, we are doing some F test, right? So one-way ANOVA, multiple group comparison, right? So in here, equal variance are assumed in first line, and the second line, equal variance are not assumed. So look at the significant level, 0.05. We conduct this analysis based on the alpha is equal to 0.05. What about this p-value? What it says to you?
Since it's less than 0.05,
Okay.
it is significant. So that means we can reject the null hypothesis and maybe accept the alternative one.
You can reject the null hypothesis, right? Can or
Yes.
can't?
You can reject the null hypothesis.
Yeah, you can reject the null hypothesis. That means we do have enough evidence to reject the null, right, in favor of alternative. In this case, variance are not equal, right? Variance assumed equal not works here, right? Am I right? That means variance are different, right?
Variance must be different, yes.
Yeah, variance are different because p-value is very small, right? So in that case, Levens test for equality of variance, what you can do is you can interpret your results based on the second row, right? This row. If
Yes.
this is big enough, then you can assume this one, variance are equal, right? If it's small, that's why we are concluding that equal variance not assumed. Then the significant value is 0.000 is smaller than 0.05 and reject the null, right? But in this case, your test statistics, what was the test statistic? Is one-tailed test, right? Not the test statistics, it's the alternative hypothesis is one-tailed test, right? So we are looking some 10 subject with the if the mean secretions is smaller for normal subject compared to the ulcer subject, right? So mu n less than mu u. So what about the p value for this test is half of 0. Half of 0. Where is the output? Half of this is equivalent to 0, right? That's half of the significant two-tailed test is 0 less than 0.05 indicates to reject the null hypothesis, indicates that the normal subjects, the smaller for normal subject compared to ulcer subject, right? So you will have enough evidence to reject the null and conclude mu n is smaller than mu u at the level of significant alpha is equal to 0.05. And also it's clear when you look at into the descriptive statistics, group statistics, look at this. At the normal group, the average mean is 3.75, but also group has a mean 18.976, right? Okay. So that's a conclusion of these two sample t-tests.
So when you say 5% level of significance, that means it's the same as saying 95% confidence interval, right?
Yeah.
It's the same thing.
Yeah, exactly. Yeah. So usually the interpretation is based on the level of alpha, right? Significant level of alpha. You can say that in that way as well, right? Confidence interval 95%.
So level, so when you say alpha, that means the power you're talking about, right?
No, alpha is type 1 error.
Okay.
Alpha is not a power. Beta is the power. And the 1 minus beta is the power.
Here, significance like two-tailed, it says 0.00. This is power, right?
Which one? No, that's a p-value.
Yeah, that's a p-value, yeah.
Yeah, it's not the power.
No, 0.00, two-tailed test.
P-value. Right?
Yeah, I'm getting a little bit confused between alpha and beta.
No, in the hypothesis testing, when you get the output, there is no beta involved in this output, right? The p-value, right? P-value is right.
P-value is a significance.
It's a kind of observed significant value under the null, right?
Mm-hmm.
That's why we are comparing that value with the alpha, because alpha is a type 1 error. What is type 1 error? Reject the null hypothesis when it's true, right?
Yes.
Right? Yeah. So we are attempting to reject the null even though it's true, right? That is alpha. That's a type 1 error. And p-value, the observed significant value when it's true, right? So that means observed significant value. We are trying to reject the null when it's true. So compare these two, right? So look at this significant value, 0.00 is a two-tailed test, but our research hypothesis is one-tailed test. Then half of this significant value is going to be 0.0 and is smaller than 0.05, right? So as a result, we do have enough evidence to reject the null hypothesis and conclude that mu n is smaller than mu u, okay?
Where can you see alpha here? I mean, you say type 1 error. How do you know if there is an error here or not?
That's what I chose, 95, right? So here the 95 means what? The confidence interval was 95, right? So 1 minus alpha is 95. 100 into 1 minus alpha is 95. What about the alpha?
Okay, the rest 5%.
Yeah, okay.
Okay, thanks. Yeah.
Yeah, you're welcome. So confidence interval is usually denoted by 100 into 1 minus alpha, right? So in this case, 100 into 1 minus alpha is equal to 95. Then 1 minus alpha is 0.95. Alpha going to be 0.05. Okay. Any other questions? One more example I can do that. Let me check with let me open a data set. Did I give this data set? Did you have this data set? Do you have this data set with you guys? Carbohydrate plus protein and carbohydrate. Okay, look at this data. If you don't have, it's okay. Don't worry about that. So here, these examples is related to kind of a dependent sample. That means the this is actually 10.57, 10.89, 10.17 is measured from based on the running performance, right? The running performance with the carb and protein, and running performance with only carb. So at day one, they provide a carb and they measured the running performance from an individual. And the same from the same individual at day two, what they did was they gave some additional protein with the carb, and their running performance was measured. So this is an example for dependent sample, because the observations information collected in day one and day two from same patient, right? Same individual, right? So which is an example for a dependent sample, right? So for example, if you want to make sure whether your drug perform well, or some kind of a, what do you call, maybe blood pressure medication, right? So before give a medication, measure the blood pressure, and after a couple of days, measure the blood pressure once they had a drug, right? And these measurements taken from the same individual, right? So before and after. So in order to test efficacy of the drug, right? So this test can be conducted using a match paired, because independent samples involved in this case, right? So equal number of observations before and after, all right? So in this experiment, the researcher would like to know whether carb protein performed very well. That means whether if they introduce carb and protein together, the runners perform better than when they had carb, right? So in that case, you have to subtract this information from one to another, right? So create the variable, say di. So transform, compute, I would say difference, right? What is difference? Difference is subtract the information from carb to minus protein. That is going to be, sorry, that is going to be in your okay. This is the difference, right? The carb minus, okay, difference. Now, in this case, if you are planning to do testing or statistical testing manually, so you have to do one sample t-test for the difference variable, not for these two. But in SPSS, how do we analyze this one? Compare it's a match paired sample t-test because dependence. So select the carb first and second carb plus protein and see whether we do have any difference between those two samples, right? So this is carb minus carb protein, right? So in that case, carb minus carb plus protein must be less than 0, right? So that means then mu d must be less than 0. So mu d in the sense a different population mean in the difference, right? So mu d is equal to 0 versus mu d less than 0. Mu d less than 0 in the sense the mu d less than 0 in the sense time in the carb plus protein is smaller, less than 0, not less than 0, greater than 0. Then time in the day 1 with the carb, on average time day 1 in the carbohydrate, on average, running average is bigger than the running average in the day 2 with the carbohydrate and protein, right? In this case, look at the significant level is 0.01. And here we are checking one tail test, testing versus equal. So in that case, the half of this p-value is going to be 0.005. That is less than or equal to alpha 0.05, right? Indicates reject the null hypothesis. That means carb plus protein, giving a carbohydrate plus protein perform better than the giving only carb in running performance. Okay, so in this case, in the running performance, in the sense you need to complete the target within a shorter time period, right? Am I right? No answers. No one is here.
I'm not sure, like, is it in the problem statement in the research question?
No, because if you want to, by providing two different kind of boost, right? So we need to know which one perform, which one actually perform in the running performance, right? That means running performance in the sense you have to reach the target very short time period, right? Okay.
Okay.
So that's the main concern. So carb minus carb plus protein is bigger than 0, right? So mu d difference is bigger than 0, right? So in this case, p-value is 0.005, less than 0.05, indicates to reject the null hypothesis, indicates the carb plus protein perform better running performance than only having a carbohydrate. Okay, that's the interpretation. Any other questions?
So
Yeah.
null hypothesis in this case would be carb minus carb plus protein.
So that is mu
0.
d, the difference, right? This
Yeah,
is
mu
looks
d
like
is
once
mu d is equal to 0, right?
less than or equal to 0.
Yeah.
Okay.
Yeah.
Yeah. The alternative hypothesis is mu d greater than 0. Okay.
Okay.
So in this case, so far we have discussed some kind of a hypothesis testing. I took 3 different scenarios, right? 1 sample test, 2 sample test, as well as paired sample t-test, right? So similar way you can do a multivariate ANOVA, right? 1-way ANOVA, 2-way ANOVA. Not only that one, you can do other statistical analysis as well, right? So chi-square test comparing two categorical variable to see whether there is any association exist or not, right? So Pearson chi-square test or exact Fisher's exact test, right? So that kind of analysis can be conducted in SPSS, and also this SPSS will help you to do some advanced level statistical analysis as well, right? So not only hypothesis testing, you can fit a regression model, multiple linear regression model as well. So that can be done. Go to the analysis generalized linear model, and not the generalized linear model regression. And in the regression, select linear, or right, linear, and keep them information corresponding that which one is going to be the dependent variable and which one going to be the independent variable, right? And also you can fit the logistic model. Why logistic model? When your response are dichotomous, right? So binary outcomes. Your response are binary outcomes, then you have to have a model called logistic model. Regression model is helpful when you have an outcome with a continuous manner, right? So that's all I plan to discuss in today introductory level SPSS course. In future, if we continue this program, we can go further in a little bit advanced level of the analysis programs, such as linear regression, correlation, and multiple linear regression, stuff like that. Okay. Any other questions?
Do you have some free resources or some suggestions for us?
Free resources, you mean?
Yeah, or yeah, or any suggestions where we can get more information or learn more about?
Just Google it. You might find any other sources, because there are so many YouTube channels, right? People used to post stuff on the YouTube as well. Depends on your query, right? For example, if you want to learn something about the two sample t-test, just type two sample t-test. You might get some resources to explore, right? I'm not sure free resources for the SPSS, even though SPSS is not freely available nowadays. Instead of SPSS, you might handle this kind of information in R as well, right? R is freely available. You can play around, right? Can you explain Spearman and Pearson correlation analysis? So the Pearson correlation analysis is meant for discrete cases, right? Pearson correlation analysis can be conducted to see whether two variables, is there any association or dependency between two variables, right? So this, any example, I don't have a data set to explain that one at the moment. If you really need it, I can pass it through proper channel for you guys in a couple of days, right? So if I get any data set to explain the chi-square test, okay? Sorry, Dr. Sarwar.
Thank you so much, Hensley. Are there any other questions?
No problem, yeah.
I did put the link for the R software in the chat if people are interested in playing around with R, since it's free.
Yeah. So that is the only software freely available. You can play around, but the R is not like SPSS. SPSS especially itself has many drop-down many commands. So you can easily play around in SPSS, but in R, you have to write syntax, especially step-by-step commands to execute the program. Even though for a mean, not like SPSS, in order to get the descriptive statistics, you have to type something as summary of the variable, right? Something like that.
Right.
Yeah. Yeah, SPSS is for a fundamental study. SPSS is good enough, more than good enough, even though you can do advanced level analysis as well. you don't need to worry about the R. You can do that kind of an advanced analysis in SPSS. Only thing is it's license required, right?
There's another question here from Dr. Sarwar.
Yeah,
So Hensley, I guess your email address would probably be best.
Yeah, sure. Yeah, the questions, and you can definitely please contact at hensley.mariathas@med.mon.ca anytime. Yeah, if you need any help. Yeah. Yeah, thanks, Chelsea. Yeah.
Oh, thank you. It's
Yeah.
very, I mean, it's much easier to do these kinds of workshops in person when you can walk around the computer lab, but
Yeah.
hopefully it seemed like from the discussion that people were getting some good feedback and an opportunity to practice. So we really appreciate you doing this webinar for us, Hensley.
Oh, no problem. Yeah, you are very welcome. Yeah.
Does anyone have any other questions before we wrap up?
Thanks very much for the presentation. It was nice to learn. Thank you.
Oh, thanks anyway. Yeah.
Thank you all for joining us.
Yeah.
I'm going to I'll just quickly add my email to the chat box as well. And then that way, if anybody has any further questions, please feel free to email either Dr. Mariathas or myself.
Yeah.
And we'll make sure that they get answered one way or another. And as I said previously, the recording for this session should be available in the next couple of weeks on our training page. And if you scroll through the chat, you'll find that as well.
Do you have more workshops coming up?
Yeah, absolutely. Well, not this year, I don't think. We're just wrapping up our training program for the year, but we do offer free training monthly. So please, absolutely, please keep checking out our training page of our website. I'll repost that here in the chat. You can also, on the main page of our website, sign up for our training newsletter and stay up to date on what we're offering and some opportunities through our unit, through that newsletter.
Thank you.
No problem.
And also unit offer some certificate program as well, right?
Yeah, that's right, Hensley. Thanks for that. Yeah, no, if you complete 6 sessions in any 2 calendar years, then we will issue you a letter of completion for our patient-oriented research training program.
This year you are wrapping up, right? So this one would not count.
Yeah, sure, it would count. And then if next year you decide to do 5 more sessions, then you'll get your letter of completion.
Thank you.
Yeah. Okay, well, if there's nothing else, I'll just say thank you again to Dr. Mariathas for this wonderful workshop and for taking the time to teach us all about SPSS. And thank you all for joining us from all over the place, it looks like. And I hope you all have a great evening.
Hey, then, thanks.
Thanks.
Bye.
Bye.